Hi, this is A. Somaiah working as assistant professor in the Department of Mechanical Engineering. So, welcome back to the fluid mechanics and hydraulic machines. Today, the topic is major and minor energy losses. So, there are while the fluid is flowing from one point to another point through a pipe or through canal or through channel, so there will be a number of losses will be existing. The losses can be classified into major and minor energy losses. When the fluid flow is taking place through a pipe, and due to the friction, the major energy loss will be taking place, and the major energy loss can be calculated by using Darcy's Weisbach equation, and another equation is Chezy's formula. So similarly, there are minor energy losses also while the fluid is flowing through a pipe from one point to another point. There will be different cross sections of pipes will be there. When the fluid is suddenly expanding from one diameter to another diameter, bigger diameter, that case is known as sudden expansion. And another one is sudden contraction, when the diameter is contracting from bigger diameter to smaller diameter. And when there is a bend in a pipe, so there will be loss again. Therefore, this type of loss is known as bend. Due to bend, the loss of energy due to bend in a pipe. So this is classified as a minor energy loss. Also, due to pipe fittings. Also, that is a minor energy loss. Another one is there is a if there is any obstruction in a pipe, also you can call it as minor energy losses. So basically, when your fluid is flowing from one point to another point through a pipe, so because as we are discussing the flow closed conduit flow, the closed conduit flow means the fluid is always running through a pipe only, not through open channel or canal. So therefore, while the fluid is flowing through a pipe from one point to another point, then there will be different types of losses. Those losses can be classified into major and minor energy losses. But if the loss is going to occur due to the frictional loss, due to frictional resistance. So when your fluid is flowing from this pipe from this point to point 1 to point 2, so there will be frictional resistance. Always there will be frictional resistance. Due to frictional resistance, there will be pressure difference. Here pressure P1 will be there due to frictional resistance. Due to frictional resistance, the pressure drop will be occurring. So that means there is a energy loss will be taking place. So this type of energy loss comes under major energy loss. So similarly, the minor energy means these are the examples when a pipe cross section is varying from one point from diameter, while so small diameter to bigger diameter, or bigger diameter to small diameter, or if there is any bend in a pipe, or if there is any obstruction in a pipe, such type of losses will be coming under minor energy losses. So, whenever the fluid is flowing from one point to another point in a pipe, in a closed conduit, the losses will be also significant due to frictional loss. These are significant. That's why we need to measure. So there will be the derivation for the measurement of frictional loss of head. What is the head loss due to the friction? So that we can be calculating by using Darcy's Weisbach equation. Similarly, Chezy's equation also. Chezy's empirical formula is there. Using that Chezy's formula also, we can calculate. We can measure the loss in a head. So while the fluid is occurring from one point to another point. So now we are going to derive an expression for major energy loss, which is derived by which is slated by Darcy Weisbach. This is also known as Darcy's Weisbach equation. So before going to derivation, we have to consider a pipe. So of uniform diameter, pipe of uniform diameter, and say this is a cross section 1 and say cross section 2, and the fluid is flowing in this direction. So the pressure force will be acting on section 1, P1 into A, and if this is a control volume, you consider this as a control volume, and always against to the flow direction, the P2 will be acting P2 into A. So towards the control volume, always pressure will be acting, pressure force will act towards the control volume. Therefore, at section 1, P1 into A is the area into pressure is nothing but pressure force at section 1, and similarly P2 into A will be the pressure force at section 2. So this is the control volume through which fluid is taking place, and in between section 1 and section 2, consider and the pipe length as a L. It is assumed as L. So in this control volume, how the pressure is going to be reduced, and how the frictional loss due to the head loss due to the friction, how it can be calculated. So that we will see now. So we are going to consider a horizontal pipe, and through this there is a fluid flow is occurring. Consider length as L, and on these two sections. So whenever we are going to consider these two sections as Bernoulli's statement, the energy, the total energy at section 1 is a constant, is equals to total energy at section 2. That means always the total energy remains constant in a ideal flow and in a steady flow. So in this type of flow actually doesn't occur. But Bernoulli's statement states that the total energy remains constant while the fluid is flowing from one point to another point. So wherever you measure, the total energy remains constant. That is Bernoulli's equation. But we are going to apply Bernoulli's equation in this real case. We are going to apply a real fluid for which we are going to derive an expression for the head loss due to friction. So therefore, we are going to apply Bernoulli's equation for real fluid. So in this case, while you apply Bernoulli's equation in a real flow, real fluids, and while the real fluid is flowing through a pipe, so these are the two sections while fluid is passing from section 1 to section 2. So in these two sections, we are to consider the various parameters like pressure at section 1 P1 and pressure at P1 and V1. Similarly A1 etc. Similarly P2, A2, V2 etc. These are the parameters at section 2. And as the diameter is uniform, as the cross section of the pipe is uniform, so therefore velocity we can consider V1 equals to V2, and from the elevation both are at same section, Z1 and Z2 are also equal. So from the bottom line both are at same level, therefore Z1 is equals to Z2. So as per Bernoulli's statement, we can write P1 by rho G plus V1 square by 2G plus Z1. So that means pressure head, velocity head and potential head, these three heads are constant. The summation of these three energies or three heads is equals to the same energies at another point, at another section, P2 by rho G plus V2 square by 2G plus Z2. The same parameters as section 2. So this is the Bernoulli's equation. Actually up to this is a Bernoulli's equation for a ideal fluid. So because total energy remains a constant at any section, but in case of real fluid always it is associated with a real material, and real fluids so that there will be a friction and viscosity. So due to all these losses, the total energy may not remains the same at any point. Always due to the friction, the pressure drop is going to take place. Therefore, the total energy always it is going to deviate in the direction of flow. So therefore, we have to add the loss of energy due to friction also. So therefore, we can write the Bernoulli's, we can state the Bernoulli's equation for a real fluid as total energy at section 1 is equals to total energy at section 2 plus losses. So the losses may include the major energy loss and minor energy loss. You can add the HF indicates the major energy loss. Also minor energy losses also can be added, but here the purpose is we are going to derive loss of head due to friction. The major energy loss we are going to derive. So this is a main parameter which we are going to determine from this. So this is a main parameter. So by utilizing the Bernoulli's equation for a real fluid in a real case, so we are going to derive loss of head due to friction. This is the parameter we are going to derive. So as V1 is equals to V2 and similarly Z1 is equals to Z2, so these two parameters can be eliminated. Therefore, so what we have P1 by rho g minus P2 by rho g is equals to loss of head due to friction HF. It is becoming HF. So this is equation 2. So the HF means loss of head due to friction is equals to the difference of pressure heads between section 1 and section 2. So simply we can state loss of it due to friction like that. So furtherly, during in further consideration, it can be reframed and otherwise it can be derived in this way. The pressure intensity will be reduced by the frictional resistance in the direction of flow. So always in the direction of flow, the frictional resistance will be occurring. So as the length is increasing, the frictional drop is also going to be increased proportionately. And the difference of pressure heads between two sections is equal to the loss of head due to friction between these sections. So therefore, we can define HF is equals to P1 by rho g minus P2 by rho g. So we have to consider F dash. F dash is nothing but a frictional resistance per unit area at unit velocity. So then frictional resistance can be written as F dash into area into V power n. F dash into area into V power n, where the F dash is nothing but a frictional resistance per unit area at unit velocity. That is nothing but F dash. We have to consider, we have to assume F dash is frictional resistance per unit area per unit velocity. So therefore, it becomes F dash into area into V power n, where area of the flow, while the fluid is flowing from your pipe, the perimeter of the pipe is nothing but P and the length of the pipe is L. So P into L becomes the area, F dash into PL into V power n. So this is the frictional resistance where P is wetted perimeter of a pipe. So now pressure forces at the sections 1 and 2 is nothing but P1 into A, P2 into A. So that we have seen in the previous slide. At section 1 and at section 2, these are the control volumes. Then we can consider the pressure force at section 2 is P to A is acting towards control volume. Similarly, P1 into A is the pressure force at section 1. So towards the control volume. Thus resolving the forces. So resolving the forces on the consider the pipe the section at section 1 and 2. So if you resolve it horizontally, we will have the pressure force at inlet is P1 into A. This is equals to P2 into A plus frictional resistance. Here frictional resistance can be added. The same thing is written here. P1 into A is equals to P2 into A plus frictional resistance, where frictional resistance is nothing but F dash into area into V power n. So from this we can write P1 minus P2 into A is equals to F dash into PL into V power n, or P1 minus P2 is equals to F dash into P by A. So P by A into L into V power n. So we can write like this. So now we are making only the difference of pressure we are determining. Therefore, it becomes F dash P by A L V power n. Now dividing either side with the specific weight. The specific weight is equals to rho g. Specific weight is equals to rho g. But I am dividing both sides with rho g. Then we will get P1 by P1 minus P2 by rho g is equals to F dash by rho g into P by A into L into V power n. Here another consideration is that we know this P1 minus P2 by rho g, while applying the Bernoulli's equation, we came to know that P1 minus P2 by rho g is equals to HF, loss of head due to friction. So now I am going to substitute loss of head due to friction HF over here. Now another consideration is that P by A. So basically A by P is known as hydraulic radius or hydraulic mean depth. So here we can define hydraulic radius is known as A by P. So here A by P, if you utilize A by P, the A is the area and P is the perimeter. 5D square by 4 by 5D. This is D by 4. This is M equals to D by 4. But this is nothing but A by P. But in previous equation we got P by A. So this P by A is nothing but we can replace this one with a small m. With a small m. 1 by m. This is equals to 1 by m. We can replace P by A with 1 by m. So therefore, the equation can be written like this: HF is equals to F dash by rho J into LV power n by m, small m. This is nothing but A by P. So here A by P is nothing but D by 4. Now I am going to substitute m equals to D by 4 in the equation 5. So because the A by P is known as hydraulic mean depth. So we know area and perimeter. So if you substitute D by 4, we can write the equation like this: HF equals to 4F dash by rho G into LV square by D. So where I am taking n equals to 2, assuming n equals to, it will vary maximum of 1.7 to 2. So therefore I am taking the n equals to 2. So therefore it becomes LV square by D, 4F dash rho by F dash by rho G into LV square by D. So here F dash by rho G, another consideration is that 4F dash by rho G can be equals to, by experimentally it can be written like F by 2G. It is assumed easy 4F dash by rho G is taken as F by 2G. Experimentally it is written like this. Therefore the entire equation can be substituted. 4F dash by rho G is substituted with F by 2G. Therefore the equation becomes HF equals to FLV square by 2GD. So this equation, in this, F is known as friction factor. So now loss of head due to friction, HF is equals to loss of head. So loss of head due to friction, loss of head due to friction. Loss of head due to friction is nothing but HF always. So the expression is equals to FLV square by 2GD, where F is known as frictional factor. So here this equation can be written as 4FLV square by 2GD also. This equation can be written as 4FLV square by 2GD. That means 4F dash by rho G equals to 4F by 2G. So that is equals to 4, then it becomes 4FLV square by 2GD. So in that case, where F is known as coefficient of friction. Coefficient of friction. So this is the difference between the FLV square by 2GD and 4FLV square by 2GD. So when these two equations indicates the loss of head due to friction, this is also known as Darcy-Weisbach equation. This is as per Darcy's consideration, Darcy's Weisbach equation. So Darcy-Weisbach equation is nothing but HF equals to 4FLV square by 2GD or FLV square by 2GD. So in this, so if it is FLV square by 2GD, where F is known as frictional factor, friction factor. But if loss of head due to friction can be written also 4FLV square by 2GD. In that case, F indicates, F will be defined as coefficient of friction. So this is the derivation for Darcy's Weisbach equation. Also, this is the derivation for major energy loss. Major energy loss. So in the 4FLV square by 2GD, this is equals to coefficient of friction. If only F is definition will change, F definition will change, F equals to 4FLV square by 2GD. So in that, F is nothing but coefficient of friction. So where, so F equals to 16 by RE, its definition will vary. F equals to 16 by RE and F equals to 0.079 by RE power 1 by 4. So these definitions will be based on Reynolds number. If the Reynolds number is less than 2000, that is known as laminar flow. So that is experimentally proven. So the Reynolds number is nothing but ratio of inertia forces to viscous forces. Rho Vd by mu or Vd by nu is equals to Vd by nu or rho Vd by mu. So if you substitute velocity and diameter, kinematic viscosity of the fluid, If the value is less than to 2000, then F is equals to, you have to utilize this relationship 16 by RE, 16 by RE. So if it is varying from 4000 to 10 power 6, that means above in turbulent region, above 4000 is a turbulent region. In that region, if you are going to find F Reynolds number is more than to 4000, so that is equals to rho vd by mu or vd by nu. If the value is above 4000, then greater than to 4000, then you have to use coefficient of friction as 0.079 by Re power 1 by 4. So this is a relation you have to use if the Darcy's Weisbach equation is 4FLV square by 2GD. If it is FLV square by 2GD, the F indicates coefficient frictional factor, but 4FLV square by 2GD, in this it will be known as coefficient of friction that can be derived, but it can be used, the F can be calculated by using these two relations. The F can be used by using these two relations. So for laminar flow, this is a relation. For turbulent flow, so 0.079 by Re power 1 by 4. So this is the relation for a turbulent flow. So the equation 6 is known as the Darcy-Weisbach equation, which is commonly used for computing the loss of head due to friction in pipes. So actually the Darcy-Weisbach equation is derived and by assuming the which is flowing through a pipe by utilizing the real fluids, and whenever it can be used for for computation of loss of head due to friction. It may be noted that the head loss due to friction also expressed in terms of velocity at v square by 2g corresponding to the mean velocity. Further, the observations show that the coefficient F is not a constant, but a value depends on the roughness condition of the pipe surface, Reynolds number, etc. So the F coefficient of friction and frictional factor, these parameters will vary based on the Reynolds number. Coefficient of friction is associated with a Reynolds number. So in the Darcy-Weisbach equation, if HF equals to 4FLV square by 2GD, 4FLV square by 2GD, this is known as coefficient of friction. This is associated with a Reynolds number, and frictional factor is always associated with a pipe surface, where you can use FLV square by 2GD. As such, in order to determine the loss of head due to friction correctly, it is essential to estimate the value of the factor F correctly. Now, this is a Darcy-Weisbach equation is one of the major energy laws. One is Darcy, another one is Chezy's also. We can use Chezy's equation to calculate the major energy loss. So the Chezy's equation is V equals to C into root mi. So the HF equals to 4FLV square by 2GD is the Darcy-Weisbach equation by which we can measure the major energy loss. Also, another two equations are there. There is one is Chezy's formula and another one is Manning's equation. So in Chezy's equation, so V equals to C into root mi. So here, if V is here V indicates a velocity. V is nothing but velocity, where C is a Chezy's constant, or root 2g by f. This is nothing but root 2g by f. Also, sometimes it can be provided as Chezy's constant value will be provided. So where m is equals to A by P, hydraulic mean depth, and where I equals to HF by L, loss of it due to friction upon length. So HF by L. So by using all these parameters, we can also calculate major energy loss by like Darcy-Weisbach equation. So in the Manning's formula also, we can use Manning's formula for calculation of major energy loss. So it is the most common formula which is mostly used for analysis of the problems. of flow through channels, but often used for the analysis of high flow problems too. So according to this formula, where V is velocity is equals to 1 by n into r power 2 by 3 and s power 1 by 2. So where n is the Manning's roughness, n indicates the Manning's roughness, and r is hydraulic radius, s is nothing but slope of the hydraulic grade line. So hydraulic gradient line and total energy line, based on that we can calculate the slope of the line. So this is also used for the major energy loss. And one of the example for calculation of the major energy loss by utilizing the by above equations, Darcy-Weisbach equation we have seen, and also Chezy's equation also we have discussed. So based on that we have to solve this one of the example. Find the head loss due to the friction in a pipe of diameter 300 mm, length 50 meters, through which water is flowing at a velocity of 3 meter per second. So here velocity is provided and diameter is given. So you have to utilize the Darcy-Weisbach equation and also Chezy's equation to calculate the major energy loss. Here the Chezy's constant C is given as 60 and the kinematic viscosity nu. So nu is given as 0.01 Stokes. So this is a given information, diameter and the length of the pipe, velocity, Chezy's constant and kinematic viscosity. So we know the Darcy-Weisbach equation. Darcy-Weisbach equation for major energy loss is HF equals to 4FLV square by 2GD. So here we have to determine the value of F. F will have two different relations for laminar flow and for turbulent flow. If it is lower than to the 2000, then that is 16 by RE. Otherwise, if it is greater than to the 4000 in turbulent flow, so we can use 0.079 by RE power 1 by 4. So we have to utilize that equation. So in order to find which type of relation you have to choose, so in order to choose the particular relation, you have to calculate a Reynolds number. Reynolds number is nothing but Vd by nu or rho Vd by mu. So it is a ratio of inertial forces to viscous forces. Here velocity is given as 3 meters per second, and also diameter is given as 300 meters, 300 mm. So therefore it becomes a 0.3 meters. So then kinematic viscosity is 0.01 Stoke. So 0.01 Stoke into 10 power minus 4 meter square per second. It becomes 10 power minus 4 meter square per second is equals to 1 Stoke. So therefore the Reynolds number is 9 into 10 power 5. Therefore it is absolutely a turbulent flow. If it is turbulent flow, the relationship we have a 0.079 by RE power 1 by 4. So in this we have to substitute the Reynolds number. RE is Reynolds number 9 into 10 power 5. So from this we will get F, coefficient of friction as 0.00256 is a coefficient of friction, and we have other parameters too, like length, velocity, G is known, and D is the diameter of a pipe. All these parameters we have. So once if you substitute into this equation, we will get HF equals to 0.7828 meters. The loss of height due to friction in terms of meters is 0.7828. So this is with the utilization of Darcy's major energy loss with Darcy expression. Similarly, we will calculate using Chezy's formula also. Chezy's equation is V equals to C into root Mi. So where M equals to D by 4, nothing but M is hydraulic mean depth, M equals to A by P. So that is area by perimeter, where we will get a D by 4. D is the diameter. Diameter is 0.3 meters. 0.3 meter by 4, 0.075 meters. And Chezy's constant C is given as 60. Otherwise, C equals to root 2G by F. We have to utilize this relation also. So therefore, we can substitute as all the parameters are available. So and we know I is nothing but HF by L. So from this, loss of height due to friction can be calculated. In order to calculate loss of height due to friction from Chezy's, we have to calculate first of all I. Once I is known, H can be disclosed. So I equals to 0.033. Therefore, I equals to HF by L. From this, HF equals to 1.665. So loss of eddy due to friction using changes is 1.665, and 0.7828 is through Darcy's. This is Darcy's result. So by using these two equations, we can calculate loss of head due to friction. We have to measure the loss of major energy loss, how much it is lost. So in terms of these equations, we can measure like this. Now, coming to the minor energy loss. Minor energy losses means when the pipe cross section is going to vary from the one diameter to another diameter, otherwise due to elbow or due to pipe bend or due to pipe friction, due to some fittings in your pipe, otherwise some obstruction in your pipe. These are all known as loss of head due to minor energy losses. These are all called as minor energy. So this is an example of when a fluid is flowing from a smaller diameter of a pipe to a bigger diameter of pipe. While it is flowing like this, the difference, if there is a uniform diameter, there is no loss. But when a diameter is going to increase like this, then there is a separation, some portion separation will occur. So these two triangular portions, the area of these two triangles will be a loss of energy, because while the fluid is flowing from the minimum diameter, some lower diameter to bigger diameter, the flow may not attain the full cross-sectional area of a bigger diameter immediately. So immediately it won't catch the complete perimeter of the bigger diameter. Therefore, after some time, it reaches the complete diameter of the bigger diameter after flowing up to this much of distance. After flowing after this distance only, it will attain full diameter. Otherwise, till that there is a separation, there will be low energy particles in these areas, and the eddies will be forming, and this much of portion is nothing but the loss of eddy due to sudden enlargement. If there is no sudden enlargement, there will be no separation. If there is a flow, this is nothing but flow separation. When there is a flow separation, there will be loss of head. Again, we have to consider two sections. So the pressure force P1 A1 at inlet, and at outlet or at section 2 at this control volume, the pressure force is P2 A2. So for this, the equation is V1 minus V2 square by 2G. So loss of energy due to sudden expansion. While the sudden expansion is going to take place, then there will be a flow separation is occurring. Due to that, energy lost can be calculated by using V1 minus V2 whole square by 2G. So similarly, while the fluid is flowing from bigger diameter to smaller diameter, this is quite opposite to the loss of eddy due to sudden expansion. In this case also, the initially fluid is flowing through this much of diameter, capital D, but it has to flow through small d. So, but what happens while it is coming into a smaller diameter, it has to separate from its outer diameter, and it is going to enter into the smaller diameter, but after some distance only, it will follow the contour of the inner diameter of a smaller pipe. So here again, the flow separation is taking place in these two portions. The flow separation at the entrance of, after entrance up to some distance in a minor pipe, there will be a flow separation will be existing, and similarly there will be a flow separation in the major pipe also. So these two flow separation at these 2 points, the flow separation will be occurring while the fluid is converting its diameter from bigger to smaller. There will be flow separation. Therefore, after this separation, gradually it is going to attain the outer periphery of a smaller diameter. So, but till now these two portions are the losses. That means a loss of energy due to sudden contraction. If it is going to contract suddenly, this is a loss. This is a damage to the energy. Energy loss will be taking place like this. So that's why, in order to prevent this type of losses, better to avoid the sharp corners. So if the stress flow lines will be drawn with a smooth curve, then will be flow separation can be avoided. The flow lines can be drawn smoothly like this, so that this portion can be eliminated. But however, there will be a separation will be there in a minor smaller dia of pipe. This will not be avoided. So therefore, the diameter goes on decreasing up to some portion. At some point, the lowest diameter of a flow passage can be taken place. So the minimum most diameter, this is known as a vena contracta. After this, gradually the flow will be diverging. So till this, there will be converging. Afterwards, there will be a diverging portion will be there. So in the divergent portion, gradually, again, the energy will be acquired, will be attained by the fluid particles. Again, it will be following the path of the pipe. So, but there is a loss. The separation is going to take place. So therefore, this is nothing but loss. So here the loss can be given as zero point 0.5 times V2 square by 2G. Loss of head due to sudden contraction can be given as 0.5 V2 square by 2G. And loss of head at the entrance of pipe will be taken place. At the entrance of pipe, suddenly there will be again flow separation will be existing. So due to that, at the entrance, when there is a sump like this, whenever the tank through which the water is flowing, at the entrance, again, the flow will be gradually decreasing. There will be a convergent portion. Again, there will be a diverging. So vena contracta will be existing. Flow separation will be taking place. Therefore, the flow loss of energy at the entrance always it will be existing. So that will be equals to 0.5 times V square by 2G. Loss of it at the exit of a pipe also. At the exit of pipe also there will be loss. So this loss of it due to the velocity of liquid at the outlet of the pipe, which is dissipated either in the form of a free jet or lost in the tank or reservoir. So therefore, when a pipe is connected to a reservoir, its outlet is connected like this. So here the inlet loss. Similarly, if it is open to the atmosphere freely, so then we won't consider the loss of energy due to exit of a pipe. But whenever it is connecting to another reservoir, so otherwise another pipe, then there will be a loss. So the exit loss will be equals to V square by 2G. Because the velocity will be reduced. The velocity will be reduced. The loss of head due to due to an obstruction in a pipe. If there is some obstruction in some foreign material, and then due to that, that much of quantity of fluid is flowing, fluid flow becomes less. So equal to that area, that much of energy will be lost. So that can be given by using H equals to V square by 2G into A by Cc into A minus 1 square. So this is a derived area of a pipe, area of a section. This is equals to coefficient of a contraction. So this by using this relation, we can calculate loss of head due to obstruction in your pipe. This is also considered as one of the minor energy loss. So next, sixth minor energy loss is due to a pipe bend. If the bend when the elbow is there like this, when the fluid is converting from this direction to this direction, the sharp edge will be there. So during conversion, momentum will be reduced and energy loss will be taken place. And if it is flow separation will be existing, and if it is a smooth curve also, there will be reduction in momentum or reduction in velocity. Therefore, energy will be lost. So due to pipe bend or due to elbow, etc., there will be loss. So that can be defined by kV square by 2G. This is indicates the bend coefficient. K is nothing but a bend coefficient into V square by 2G, where V is the velocity of a fluid. So these are the parameters on which it can depend, like angle of bend, radius of curvature, and the diameter of a pipe. And another loss is loss of head due to various pipe fittings. The pipe fittings may include walls, couplings, etc. Due to that, the some of the some quantity will be reduced, the momentum, otherwise velocity will be reduced. Based on that, we can express kv square by 2g, where v is the velocity and k is the coefficient of a fitting or that material, coupling or valves, etc. These are the some of the minor energy losses. So minor energy losses may be due to sudden contraction or sudden expansion, etc., and due to obstruction, due to pipe fittings. These are all comes under minor energy losses. And major energy loss is due to only frictional loss, when the fluid is flowing from one point to another point. Frictional resistance always will be occurring. Due to that, the major energy loss will be taken place. That is given by Darcy-Weisbach equation and Chezy's formula, Manning's formula, etc. So these are the classifications and expressions for the various losses while the fluid flow is taken from a closed conduit. Thank you. These are the references.
Like, share and subscribe. Hit the bell icon for more updates.